to review for the next exam. We left off just short of number 51. So we consider the following specific heats of these metals. And if the same amount of heat is added to 25 grams of each of the metals, which are all at the same initial temperatures, which metal will have the highest temperature? The way to answer this question is to look at their specific heats and what that means. There's several ways to do it. Let's say we're going to use the formula, specific heat times mass times change in temperature. Change in temperature is where we have final temperature minus initial temperature. Okay, so they're the same masses, correct? Same amount of heat, 25 grams each, right? So this is constant. And the same amount of heat is added, so that's constant. And they're starting off at the same initial temperature. Okay. So the only thing that's going to vary are these two right here, specific heat and final temperature. So notice if we have two variables in a product relationship equal to a constant, that's like Boyle's law. It's an inverse relationship. Anybody remember that? Okay. So if this one goes up, that one has to go down. So the higher specific heat is going to be the lower temperature, and vice versa. The lower specific heat will give you a higher temperature. So if we're looking for the highest temperature, we just need to find out which is the lowest specific heat. And it looks to me like it's lead, doesn't it? Yeah. Lead has the lowest specific heat, so it's going to have the highest temperature. That's one way to look at it, mathematically speaking. The other is, what does specific heat mean? It means the amount of, look at the units of measure for specific heat. Joules per gram degrees C. It's the amount of heat that 1 gram of sample can absorb to give you 1 degree difference in temperature. So if you have the same amount of heat for each one and the same mass, then the lower value here will give you a higher value there. I like this way better. Makes more sense. All right, who's next? You skip a few. I kind of shy away from those ABCs unless I have to. I like the real world. 59. Heats of the following reactions. All right, so we got 4 reactions in there. What's the value of delta H for the reaction below? All right, this uses Hess's law. And this is going to take some doing, but we haven't done a Hess's law in our review yet, have we? All right, so we need to do at least one. All right, so I put the target equation on top right up here. P4, is it H10? No, it's O10, sorry. O10. And that's a solid. When we use Hess's law, the state sometimes is important, because when you go from one state to another, you get a difference in enthalpies. So we have to put the state up there just to be kosher. Oops. I need to add 6 PCl5s. This is a gas. Now I can put the product. NCl3PO gas. Okay. So that's our target equation. And we're looking for that value. Okay. So go to your available equations, and unless you have a preference, I just start with the first one. Which one gives you P4O10? P4O10, this looks like the second one, number 2, but it's backwards. All right. We have to flip that equation and put the P4O10 on the left-hand side. But fortunately, that equation only has 1 mole, and this one only has 1 mole. So all we have to do is just flip it. So we'll use the second equation and put P4O10 on this side. And let's see, and then P4 on this side, which should be a solid, and 502. 502, yes. Now the value for delta H in this case is going to be the reverse sign because we flipped the equation. So it'd be positive 2967.3. And this is in kilojoules. You ought to pay attention to that also. Okay, so we've used number 2. All right, that takes care of this one. How about PCl5? Which one has PCl5? Number 3. PCl5, number 3. But it also has to be flipped. There are 6 PCl5s. So we got to do 2 things. We have to invert the equation and multiply by a constant. So I'm going to write it up here, flipped first, and then multiplied. So we start off, let's put it over here underneath this. PCl5, that is a gas. Yep. And that's equal to PCl3, which is also a gas, plus Cl2. Yes. Okay. Now we're going to change the sign to a positive 84.2, but we're also going to multiply it by 6. 6, 6, 6. So we need to take that value and not just change the sign, but multiply it by 6. 84.2. Which is 505.2. Okay. So that takes care of this factor. Now, how about Cl3PO? Cl3PO is the 4th one. Okay, is it on the correct side? Yep. But there's only one of them. So we have Cl3PO, yes. And on this side, we have PCl3, gas. And we start off with a half, an O2. But we have to multiply it by 10. So since this is on the side that's in the equation, we don't change the sign, but we do have to multiply it by 10. So I'm going to go ahead and do that one, 285.7 negative 2857 kilojoules. Okay, now we're going to multiply everything by 10. We get 10 here, right? 10 here, and 10 times a half is what? That's a toughie. 5. Okay. So we've got all of these factors covered. And that one's due there. This one's due here. And that one's due there. Now we've got these extra factors in here. Can we cancel any of them yet? PCl3, we could cancel some of those. That wouldn't get all of them. We can cancel some of the, so we can't cancel the chlorines. We can cancel these oxygens, right? One on that side and one on this side. But now we got to get rid of, let's take it in logical order. P4. We need to put P4 on this side. Which one's got P4 in it? The first one. So P4 solid, that will take care of the P4. 6Cl2 gas yields 4 PCl3 or PCl3. Yes. And we didn't have to change anything. So we just put the value as written. Minus 1,225.6 kilojoules. And that will get rid of this one, and it'll also get rid of the chlorine. Okay, how about four PCl3s? Well, let's see, we've got 4 PCl3s and 6 PCl3s here. So 4 and 6 is 10, cancels those 10. All right, so what do we got left? That's it, right? Those are all gone. Gone. We got this one. We got that one. Nothing left over here. This one here. Cancel, 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 cancel. We're good. We just have these factors are left standing. So now we can add all those values together and get our delta H. Let's see. Change the sign. Did I do that one right? Number 4. Yes. Just checking my numbers. And 1, 2, 6. And 2, 9, 6, 7, 3. So I get minus 610.1. Okay. It takes a lot of work, I'll admit. So you have to be very methodical about it. Any questions? All right. Let's see. Let's get a few. 68. Choose the correct equation for the standard enthalpy of formation for CO. Okay. Standard enthalpy of formation. So when you're doing a standard enthalpy, you start on the product side with the compound of interest. CO, gas. And this has to be 1 mole. That you can't touch that now. Now on this side, you form that from its most stable elements. Carbon is going to be graphite. Okay. And oxygen is going to be the diatomic gas. So that's already 1 mole there, 1 mole there. This one needs, we only need half of that one. Like that. And the delta H formation is minus 110.5 kilojoules per mole. So that means that C would be the best answer for this. Okay. And let's see what's next. $78. Okay. Little logic instead of number crunching. One of the main advantages of hydrogen as a fuel is what? Well, we don't have any oddballs in there. So if we're looking for the main advantage, the only product of hydrogen combustion is water. That's true, right? Hydrogen gas plus oxygen from the air yields water under standard conditions. So we only need half of this one, or we can say, let's see, 2 here, 2 here. Right, A is a good answer. It exists as a free gas, makes no difference. Economically supplied by the world's oceans. Well, that's an advantage, but it's not the main advantage. Plants can economically produce hydrogen, not really. It contains a large amount of energy per unit volume of hydrogen gas. We didn't cover that actually. There are other fuels that are more energy dense than hydrogen. I mean, just like kerosene, for instance. So that's why when you're talking about unit volume of gas, kerosene is more energy dense because it's a liquid. So that's why in rocket engines, they take hydrogen and turn it into a liquid and fill up the tanks. That's why when you see the tanks filling up, you see a frost line going up the outside of the rocket because it's so cold. But the main advantage is simply that it produces water upon combustion. $79. Which of the following is not being considered as an energy source for the future? Okay. Well, ethanol is already here. Methanol in some applications is here. Seed oil, yeah, they're all considered energy sources. Shale oil. Carbon dioxide can't be a fuel. Carbon dioxide is a product of combustion. And we haven't talked about redox equations in that kind of detail yet, so I can't give you those explanations. But carbon dioxide, you can't burn carbon dioxide, right? It's already there. We did oxidation states, didn't we? Yeah, okay. So look at the oxidation state for carbon. If oxygen is -2 each one, -4 total, carbon is a +4 oxidation state. That's as high as it can go. You can't, if you want to burn something that's carbon-based, the carbon needs to be less than 4. So methane would be a good example, like Elon Musk's rockets. They use liquid methane. Then +1 each one of these, +4 total, -4. That's good. Combine it with oxygen, you go to there, transfer those electrons, and you can get a lot of energy out of it. That's the short version. So carbon dioxide is not being considered as fuel. All right, let's see. We'll skip a few. Let's skip a few. How about this one? Number 90. A gas absorbs 188 joules of heat and then performs 310 joules of work. Okay. The question then is, what's the change in internal energy? Change in internal energy is equal to what? Only two ways to change internal energy: heat and work. Remember that equation? Okay. So everything that happens, all numerical values that are applied to this system are that their sign of the number is based upon the system. So anything going into the system or done to the system is positive. Anything that the system does on its surroundings is negative. So when it says 188 joules of heat, gas absorbs 188 joules of heat. 188 joules. That's a positive. It goes into the gas. The gas is the system. And then performs 310 joules of work. It's losing that work because it's doing work on its surroundings. So now that we know our signs are correct, we have, let's see, 2, 3, 132, negative 132 joules. Oh, no, 122. Forgot to carry it. Like, yeah, I forgot to carry. Minor math error. Of course, minor math error caused a Mars probe to crash into the planet. Remember that one several years ago? One of the subcontractors was using, I think it was metric system, and we were building the rocket with the English system, and they forgot to make the conversions. So when the rocket got close to Mars, it got too close to Mars. Oops, we lost the signal. Things that make you go, Somebody probably got, well, I don't know. If they were government employees, they probably just got a slap on the wrist. If they were private industry, they get fired. 99. All right, nitric acid, HNO3 was first prepared 1,200 years ago by heating naturally occurring sodium nitrate, called saltpeter, with sulfuric acid to produce sodium bisulfate and collecting the vapors of HNO3. And the equation's down there below. So calculate the delta H of this reaction. Okay, this one's really easy, actually. You just need to know what's the equation that governs the production of nitric acid. And that's saltpeter, solid, yeah, solid, plus sulfuric acid. They're saying it's liquid. I wonder if it could be. We used to use sulfuric acid that was 98%. But I've never seen it 100%. That'd be kind of hazardous. But this is the Middle Ages, so sodium bisulfate is an old terminology. Anytime it says bi something, there's a hydrogen in front, like sodium bicarbonate, NaHCO3. We would now say sodium hydrogen sulfate. And then the prize, nitric acid. Okay, so if we want to determine the enthalpy, the standard enthalpy of formation, or standard enthalpy of this reaction, we can use the formation values. And fortunately, this balanced equation has 1 mole relationship. So we don't have to multiply our heats of formation by any molar factors. All we have to do is say, all right, we take the products, sodium bisulfate, which is minus 1125.5 kilojoules per mole, There's only 1 mole, so that's that one. And then nitric acid, which is minus 135.1. Minus 135.1 kilojoules. And then subtract the reactants. So saltpeter is minus 467.8 kilojoules. And sulfuric acid is minus 814. There we go. So all I have to do is pay attention to your signs. This is going to give you a negative. These are 2 negatives times a negative, be a positive. And you should come out with 221.2 kilojoules. Positive. So that means this term is going to be bigger than that term. Okay. So what kind of reaction is this? It's endothermic. Right? That's why they had to heat it. Didn't they say they had to heat it? Heating naturally occurring sodium nitrate. Yeah. Where else do we see sodium nitrate? Saltpeter. Well, sometimes they use potassium nitrate. Gunpowder. Right. Saltpeter, charcoal, and I'm missing an ingredient. Sulfur. Yeah, elemental sulfur. In the proper proportions. Set it off and it goes to town. You don't get an explosion unless you confine it. Right? If you just have gunpowder laying out in the stream on the floor, it just goes and it's gone like that. If you use gunpowder, right? Anybody load their own shells? I had a student one time who was an avid reloader. So he could tell me all I needed to know about different types of smokeless powder. But smokeless powder, you lay it out there next to gunpowder and it just goes, burns really slow. But it has a whole lot more energy in it than gunpowder does. Oh, that's it.